Hi, my name is Ayan Kumar Halder. I'm working in AMD as a member of technical staff, and today I'm going to give a presentation on porting Xen on Cortex R52. So I have been working on Xilinx ARM-based products for supporting Xen and related features for like a year and a half now. And I have a background working on ARM-based silicons for around 13 years. So I have been involved from post-silicon validation to various device drivers, power management. And I've also worked in IPs like the Ethos Neural Processing Unit IP, the Mali Display Processor Unit IPs, and all. So, in a nutshell, my background is related to software development on ARM based systems. Now, what do I want to achieve from this presentation? So, the objective of this presentation is basically twofold. I want to provide some guidance. Like, I hope that my presentation will provide some guidance to a newbie on how to port Xen on a new hardware in coordination with the Xen upstream community. This is because when I started working on this task, I was relatively new to Xen, and I hope that I could showcase some of my experience to help others who want to achieve similar goals. And I also want to gather some feedback about what could possibly be done in a better way for such an activity, because I have been working with the community now for like almost like 8 or 9 months while upstreaming different features. So definitely I would like to hear some of your opinions on this. Now, a bit about Zen. So, Zen is a type 1 hypervisor. It directly runs on top of the hardware, and it supports full virtualization and para virtualization. So, if you can see here, the main components which are configured by Zen are the timers, the serial, the interrupt controller, the memory management unit, the I/O memory management unit, PCI root complex, and it also has some kind of schedulers. And it can run various VMs as operating systems. And with Zen, you can also assign devices to particular VMs. So you can have a particular operating system using SATA, another one using GPU, and so on. So a bit about Cortex R52. So Cortex R52 is a ARC32 V8R based processor. So which means that it supports only 32-bit instruction mode and addressing mode. And it supports EL0, EL1, and EL2 mode. So it has the ARC32 execution state at each level. It doesn't have any secure mode. And it supports protected mode system architecture version 8, which means that it doesn't support memory management unit. It only supports the memory protection unit. So this is a big change compared to the traditional A class systems which are supported in Zen. It supports GIG v3. And it also supports the physical timers, so EL1, EL2, and the virtual timer. So GIG v3 is the ARM's interrupt controller, version 3. Now, moving on to what our use case is. So in Xilinx we have some mechanisms called as Xilinx memory protection unit, Xilinx peripheral protection unit, in which you could isolate the memory provided to individual processor. So, and that the memory protection unit, the peripheral protection unit, it uses the underlying embedded processor. So, any kind of configuration that happens, it has to go through the underlying embedded processor. So, we wanted to have something a bit more lightweight. So, we thought that Zen could be a good alternative to partition the system, that is the MMIO, the interrupts, the DRAM, between the two Cortex R52s. And thus, we used Zen in the DOM zero-less mode. So here the thing is the Cortex R52s are going to run some real-time operating system. So it would be very identical, but it would run on separate memory, separate interrupts. So we want to ensure that an RTOS running on a particular R52 isn't able to interfere the RTOS on another R52. So in order to achieve this, we had to port Xen on R52. So our first step was to gather the prerequisites. Now, what do we need to port a Xen on R52? First of all, we need some kind of an emulator because when we started this activity, there was no silicon or there was no in-house emulator available. So we used the Arm R FVP, that is a fixed virtual platform, as an emulator for the Cortex-R52. That also gave us an advantage because we could use the DS5 as the debugger, which is quite handy for this kind of an activity. And we wanted some kind of an OS which can be used as a DomU. So we looked for various options, and fortunately, Zephyr at that point had support for Arc32 ARM V8R platform. It had recently been upstreamed to Zephyr, so we could reuse that. And we used the Arc32 toolchain from ARM. Now, the biggest thing that we needed was the memory protection unit support in Xen, because that's the main core of it. So one of the thing that we got from ARM was working internally on developing a fork of Xen on Cortex R52 or R82. So we could reuse a bit of that. So ARM provided us a fork on the R82, and the main difference between R82 and R52 is that R82 supports the 64-bit mode, whereas R52 is strictly 32-bit mode. And the other difference is R82 supports MPU and MMU, that is the PMSA and VMSA at EL1 level, whereas R52 supports strictly MPU at EL1 level. So we could reuse a large part of the work that ARM had done internally. Now, when we got all of this, the first thing that we wanted to have was the objective that any person might have while porting the OS or the hypervisor on a new hardware, that how to get some basic prints so that at least I can use my console for debugging. So for that, we added the processor ID for the Cortex R52. We disabled the MMU and the VMSA related initialization in the early init code. And with that, we could at least get the first print cave from the Xen. And then we prepared a very minimal device tree, which consists of the memory, the gig node, the timer, the serial, and the chosen node. And once we did that, we had to read and write to the EL2 MPU regions. So as I mentioned that there were functions available to read and write to the memory protection unit regions, but that was specific for uh, Arc64. Now we had to make similar functionalities for our Arc32 mode. So once we did that, we were at least able to see Xen booting up to some level. And then the next thing that was required was we had to initialize the timers, because here our Xen is running without any underlying firmware. So it is running directly on top of the hardware. So we had to initialize the system timestamp generator. We had to configure the CNT timer, the counter frequency timer, and we had to enable the timers. Normally, these are done by the underlying firmware, like some kind of a secure firmware which runs before the system is handed over to the hypervisor. But in this case, the Xen had to take the responsibility for that. And then the next big thing was we wanted to support Gig V3. So Gig V3 was already supported in Xen, but it was supported in the Arc64 mode. So we ported it to enable the Arc32 mode. The next big thing was now in case of MPU, there is actually no translation, or I could say there is a flat translation available from the virtual address to the physical address. So which means the virtual address is identical to the physical address. So this means that normally on a 32-bit ARM 32-bit system, the physical address is represented by 64 bits. The reason being that ARM also supports the LPA, that is a large page address extension, which is 40 bits. So that's why ARM uses 64-bit to represent the physical address, whereas it uses 32-bit to represent the virtual address. Now we had to change that because we didn't want any internal truncation or any explicit truncation to happen. So for that, we had to make the representation of the physical address configurable so that user can choose whether to represent it via 32-bit or whether to represent it via 64-bit. And since Zephyr didn't support any Z image format, so we had to use an external UImage header on top of the Zephyr binary. And we had to support the probing of the UImage 32 header by Xen. And then we added the DomU nodes and the MPU specific properties to the device tree. I will show you the device tree in the later part of the presentation. And we wanted to build Zephyr. So as we said that there was a port of Zephyr available for the R32 V8R mode. And since Zephyr builds with a static device tree, so we had to change the MMIO addresses for the timer, for the TTC device, for the GIG, and the serial devices. Now, these TTC devices are the ones that we are using to test the device pass-through. So we had to use that. Now, with that, we could at least see that Xen was booting and it was able to probe Zephyr. It was able to load Zephyr. The first instruction of Zephyr got executed. But further on, we saw some problems that we were getting some kind of an instruction abort. And one of the reason was that Zephyr, it wasn't using inline assembly. So it was basically using the C code, the write-L, read-L functions to access the MMIO regions. Now, what happens is if these registers are 64-bit, so then the compiler generates LDRD, STRD instructions, um, to access the 64-bit registers. And these specific instructions aren't supported by the ARM architecture to be decoded. So basically, so normally what happens is if an instruction is accessing any of the emulated MMIO region, so that instruction gets decoded by the architecture, and then the hypervisor could actually read the instruction syndrome register to understand what kind of instruction it is, and to perform the necessary emulation which the VM has requested for. But in this case, it was giving aborts, and the Xen didn't have the emulation for the LDRT STRT instruction. So we discussed with the community, and the best course here was to basically use the inline assembly instructions to access the MMIO region. So we could use two STR instructions or two LDR instructions to access the 64-bit and 32-bit. And yes. So after that, we got that there was certain aborts because certain GigD registers weren't emulated by Xen. So that was the easiest bit. We just added emulation for those registers, and then we could um, we could we were so we prepared the partial device trees where we could pass through a TTC device to Zephyr, and we added the HVC node. So basically we didn't have more than one serials enabled. So we added the HVC hypercalls so that we could see that the interrupts are getting invoked whenever the TTC device is configured. So we could see that okay, the interrupts are getting invoked when DomUs are running. So this was all good when we were running a single DomU. So the next logical step was that we wanted to run multiple DomUs because that was our end objective. So for that, the first thing needed was R52s are by default enabled in lockstep mode because it is used for functional safety kind of applications. So one of the initial step was to disable the lockstep mode. And then we had to configure the secondary core vector address. So this actually tells the secondary core from which address to start executing its instructions. So it can be a DDR address or it can be a TCM address. So we configured that. And then we configured the reset register to boot from the vector address. So basically when we configured some bits in the reset register, so that actually tells the secondary cores, okay, now you start your execution. Yes. So with that, and then we built another instance of Zephyr, which had another unique instance of TTC device assigned to it. So we have four TTC devices in our underlying hardware. So we could use that to test our device pass through, and we could see that Xen was able to schedule both the DomUs. So once we got all our changes in place, so we wanted to upstream all the changes that we had, we had done at this point in time, because there was no need to keep like 40 or 50 patches in our own private repo. And we also wanted to get some feedback about, how the things could be done in a better way. And, we wanted to ensure that whatever we are doing is correct and doesn't use a work for me approach. So the minimal changes were there in the Zephyr. So we started upstreaming the Zephyr. So the first one was we used the 232-bit read and write for 64-bit access. That was primarily to get away with the instruction aborts. So we upstreamed that change. And then we wanted to use strictly inline assembly instructions for accessing MMIO, because we don't trust the compiler that it will always generate the correct instruction. Sometimes the compiler can be funny and it can generate like 4 LDRB instructions to access a 32-bit word. So we didn't want to do that. And in Linux and in other in Xen, we use inline assembly for MMIOs. And then we also added Z-image header support. So this happened quite late because the Z-image part was touching a lot of other architectures. So that's why we wanted to get the UImage UImage enabled in Xen, so that Xen is able to probe the UImage header correctly. And then later on, we also added support for the Z-image. And there were certain other Zephyr hacks. Now these hacks are primarily our platform specific. We are waiting for an upstream QEMU 32-bit platform to be available, and then we could reuse that in Zephyr. So then the next set of changes were the bulk, then that was the Xen changes. So here, out of all the 40 or 50 plus patches that we had, I tried to modularize it into what parts could be upstreamed without waiting for the R82 set of changes to land in. So the first thing was the gig v3 arc32 support, because so we support the gig v3 arc driver in the arc32 mode. So we upstreamed those set of changes. And then the UImage header probing was fixed. So we also upstreamed that. And then the next big set of changes was supporting the 32-bit physical address. So as I mentioned that R52 supports flat mapping, so we had to make the physical address representation configurable, and that was considered a good idea by the community, and we got that upstreamed as well. So our main idea was to reduce the set of patches which are very much core to the MPU specifics only. So remaining all, we want to get it upstreamed. And then, while discussing about the SMP part, one of the things that came to our mind was that there was no Cortex-R52 CPU node property available in the device tree. So we added that to the device tree specifications. And now most of the patches that we have in our hand is the 32-bit MPU support. So we are waiting for the 64-bit MPU support to be upstreamed, and then we could follow up on that with the 32-bit support. And now with the upstream and the things, I can show you a demo. So let me show you the device trees first. So this is basically how our Xen device tree would look like. So here you could see that there are certain MPU specific properties. That is the boot module section. This is basically where you try to load the DomU binaries. Then the guest memory section is the memory that you give to the guests. Then the device memory section is is the MMIO regions. So these are some MPU specific properties. They haven't been upstreamed, so it is still in progress. How do we represent those kind of properties? But this is currently how our device tree looks like. So we have the memory node, we have the DomU1, DomU2 nodes, And we have the interrupt controller, the serial, the timers. So we have passed through both the timers or the TTC devices. So one will be used by the first DomU, the other one will be used by the second DomU. And this is how our pass-through device tree looks like. So this is the timer that is being assigned to the first Zephyr, and this is the timer that is being assigned to the second Zephyr. And now I could show you the actual demo. So let me make it, sorry, start from here. So, so this is basically the console where you would get the logs. And we have just, so this is a command that I run, and it is trying to actually load the Xen, the device trees, the Zephyr binaries at the addresses. And here in a flash, you will see the logs. So these are the logs that you see here. You could see that kick v3 is getting initialized and all. And you could see here that it is trying to bring up the, if I can get a bit ahead. Yeah. It is trying to bring up the secondary cores here. So yeah, it's trying to bring, it has brought up the two CPUs. So it has enabled both the cores. And here you could see that it is trying to run the two DomUs. So what I have done is like I've added the hypercalls in the TTC interrupt handlers for the Zephyr, just to show that the interrupts are getting invoked. And now I'll go back to the presentation. Yeah, make it big. Okay. And one of the thing I wanted to highlight with this task is this was possible because we had an excellent collaboration with the Arm engineers. So a big shout out to Henry, Penny, Luca, Bertrand, Wei for helping out and providing the R82 bits. And they were also helping us while we were trying to do these things in a downstream mode. So this is to acknowledge that we had a great collaboration working with the ARM engineers, and we also had a great collaboration in the community while reviewing the patches. And also we had some great collaboration between the Zephyr and the Xen community, because some of the changes in the Zephyr were influenced by Xen, like the changes where we had to use inline assembly, or we had to use two LDR instructions for 64-bit register reads. So there was good collaboration between the two communities. And this is just to show the various milestones, typically how much time such a task could take. So we started with this task in March 2022. And up till now, we have got the SMP working, and we have recently been able to upstream the 32-bit physical address support. So we still have a couple of like 20 more patches which need to be upstreamed. I'm still discussing some of those patches with the community, and hopefully, yeah, we should be able to get a lot of them in the near future. And with this, I conclude my presentation. Thank you all for listening to me, and I'm open to any questions.
Hi, can you hear me?
Hi, I can hear you. Yes.
Uh, it's Bertrand from ARM. I wanted to know, why do you use specific timers inside your instead of using the architecture timer, the
These
TTC1 and
time,
TTC2? Yeah.
yes, yeah, sure. So we use these timers just to show that the guests are able to configure the MMIO, and we are able to get the interrupts. So we could have used any other MMIO devices to showcase that the guests are able to run their interrupt handlers. So we used TTC devices here because TTC devices were available. Like there were 4 TTC devices available on a platform, but internally the guests are using the ARM V8 timers. These TTC are like MMIO devices. You can take like any like SPI or UART, those kind of devices. It's like that. So we wanted to basically show that the interrupts are getting generated from the MMIO devices which are passed through to the guest.
Okay.
And does it make sense?
Yeah, it does. Thank you.
Yeah, no.
Sorry, I might not have, you might have mentioned this, but you said that first you were using inline assembly instructions to access MMIO region, but that this wasn't optimal. What did you do instead? Or did I misinterpret what you said?
Okay, no, I'll clarify it. So initially in Zephyr, they were using C instructions to access the MMIO region. So the first time when we got an issue was that some of those C instructions were getting interpreted as LDRT, STRT instructions, and those were accessing the emulated MMIO regions. So basically, Zen had to write or read to those registers. Now, ARM doesn't support decoding of LDRT, STRT instructions. So this actually, so the solution was twofold. I mean, the solution was, we had to do two things to achieve the solution. First is that remove the C instructions and use inline assembly. And the second was for 64-bit register accesses, you need to use two LDR or two STR instructions, not LDRT or STRT. So this was what we had changed in Zephyr. Uh, does it make sense?
Thank you. Yeah.
Yes.